Hi, I'm Steve Scott, Senior Vice President and Chief Technology Officer at Cray Inc. Welcome to our booth here at ISC. So we've had a busy year this year with 2 exascale contracts awarded, one to Oak Ridge National Labs and one to Argonne National Labs. Interestingly, both of these systems use the same system architecture, but different processor architectures. The Shasta system is really designed to have the same cabinet infrastructure, power and cooling, the same interconnect, and the same software stack, but be able to flexibly accommodate multiple processor architectures because we're seeing more and more diverse processor architectures come into the landscape. The Shasta cabinet architecture is quite a bit more flexible than what we've had in the past with our XC systems and CS systems. Today, and previously in Cray systems, you could either buy a CS system which has a standard 19-inch rack, it has a standard commodity software stack, and it has a standard commodity interconnect, or you could buy an XC system which has a scale-optimized rack, an optimized operating system and software stack, and a custom interconnect. In Shasta, we get rid of those distinctions. You can have either a commodity standard 19-inch rack or a dense scale-optimized rack with either an open commodity software stack or a Cray optimized software stack, and either a commodity interconnect or the Cray Slingshot custom interconnect, high-performance interconnect. So we've broken that requirement of binding the processor, the software stack, the interconnect, and the cabinet together, and we have much more flexibility in terms of the cabinet infrastructure. Additionally, our scale-optimized cabinet in Shasta is much more flexible than what we've had before in the XC system. We have the ability to have anywhere from one very large, powerful node all the way down to 16 small nodes on a compute module. We can vary the amount of network ingestion bandwidth per node as well. And we can accommodate processors going all the way up to many hundreds of watts. So accommodating a much more diverse set of processors in terms of physical size, network demands, and power demands. The software stack in Shasta is also quite a bit more flexible. We start off by having open, well-documented APIs with the ability to mix and match software. So you can use the full Cray software stack, or you can replace individual components with third-party components if you choose. The software stack also has very strong container support and support for container orchestration. So we have the ability to run just about any workload that you can run on your laptop or run in the public cloud will be able to be deployed on Shasta. We have the ability to dynamically instantiate different software environments, which means that you can spin up a Kubernetes environment for interactive analytics, or you can spin up an environment underneath a workload manager for traditional simulation modeling batch scheduled workloads. So a lot of flexibility in deploying software and a lot of flexibility in terms of how that software stack is built. We're building a brand new interconnect for Shasta called Slingshot, and Slingshot is revolutionary in 2 different ways. First of all, we've made it Ethernet compatible. So what we've done is we've married the standards-based Ethernet world with the high-performance interconnect world so that you can now have interoperability with the outside world, better to hook up to, say, third-party storage devices or ingest data from multiple outside data sources using Ethernet and IP. But then inside the network, we've done a number of things to make it a very strong HPC network. So we have an optimized protocol that we run inside the machine, which has high reliability and very high efficiency, very high performance. And we have a number of key innovations that we've added into Slingshot that we think are going to really make a substantial difference on real-world applications. We have state-of-the-art adaptive routing. We have very, very capable quality of service mechanisms so that you can overlay different virtual networks within the machine. And most importantly, we've developed an incredibly capable and sophisticated congestion control management system. And what the congestion control does is it keeps track of all the packets flowing in the network. It very quickly determines when there is congestion occurring, and it back pressures just the sources that are contributing to that congestion, allowing all of the other traffic to flow. And so it keeps the system uncongested, it keeps the latency low, it keeps both the average latency low and the tail latency low, pulling in the long tail of packet latencies. So you have very consistent low latency communication across the network. And what this does is it provides performance isolation between workloads, so that now when you run your workload one day and then run it the next day, if someone else is doing something on the network which causes congestion, it won't interfere with your workloads. And we think this is particularly important in the new world where we're having more and more heterogeneous workflows with AI and analytics and big data along with traditional simulation and modeling. So Cray now has 2 announced exaflop systems, but we actually see the exascale era as more than just reaching a certain performance level. We see it as the convergence of multiple important trends that are impacting the community at large. The first is the big data movement. More and more of our customers are being deluged by more and more data that they have to ingest and process and extract information from. We're seeing the addition of AI and analytics to their traditional simulation and modeling workloads to create these more hybrid, heterogeneous workflows with disparate sorts of computation. And we're also seeing much more variety in terms of the processors that are being used. People are now using GPUs and FPGAs and standard CPUs. They're starting to think about using AI accelerators, and so we're seeing these all come into the mix as well. So you take the big data, the heterogeneous workloads, the heterogeneous processors, put them all together, and then add to that the fact that more and more people in the enterprise space are trying to take HPC technologies and apply them to their problems in the enterprise space. And we really see some very serious shifting sands that characterize what we call the exascale era.